We got an email about band, but none of you guys are in band, are you? That's not. Okay. All right, so your unit circle, you'll need this to do all of these. So unit circle, the way that we use the unit circle is all of our x coordinates give us the sine or cosine. All the x coordinates, give us the cosine value at that point. All of the y coordinates give us the sine value at that point. So, for example, if I'm looking at number 1 here and I want to find sine of pi over 2, then I'm just on my unit circle going to go to pi over 2, and sine is the y coordinate. So I would be looking here, I'd go to pi over 2, which is here. I would look at the y coordinate for sine. So it is 1. So that tells me that sine of pi over 2 equals 1. These you can check, which you will not be allowed to use your calculator on the quiz, but if you just want to double check and it also helps you relate to what we've been doing. If you type in sine of pi over 2, actually, it's not going to work if I do this. Why is it not working? What? It's in degrees right now. So if I go to mode and change it to radians and tell it sine of pi over 3, or pi over 2, it will tell me 1. Right? So it gives you that value. So the calculator can do this for you, but we'll be doing this stuff without the calculator. So that's why we need to be able to do this. So that would be for the first one. If I want to know cosine of 5 pi over 6, I would be looking at 5 pi over 6, which is right here on the unit circle, and then I would need cosine, which is our y coordinate. So that would be negative square root of 3 over 2. So I would get negative square root of 3 over 2 here. Again, just to relate that to what we've already done, if I type in cosine of 5 pi over 6, I'm going to get this right here, which if I do negative square root of 3 over 2, I get the same decimal. Right? So it's the same as using the calculator there. Again, as I tried to explain, the main reason we're doing unit circle instead of just relying on the calculator the whole time is so that we can relate how this unit circle relates to graphs, and so we can see the nature of sine and cosine repeating over and over again there. So it's very theoretical, understanding that we're worried about having to do this. Now, we've got something tricky right here. We have got sine of negative 2 pi over 3. I'm sorry, negative pi over 3. Negative pi over 3 is not on that unit circle. Right? We only have positive values written on our unit circle. But we talked about this a little bit when we were doing vectors. The unit circle, whenever we talk about the angles, we go counterclockwise. Right? Whenever we were doing vectors, we also looked at that a little bit. If they give you an angle of 210 degrees, then that is 210 degrees counterclockwise direction. So if we have a negative angle, all that means is that we're going that distance in the clockwise direction. So when I'm looking at pi over 3, if it was positive pi over 3, it would be this far right here. Right? We'd go to that right there. But we have negative pi over 3, so we're going to go that amount, but in the negative direction, which will get us right here to 5 pi over 3. Okay? So I usually, unless the numbers get really big, I usually just think about what it looks like on the unit circle, right? So pi over 3 is this far in this direction. So if it's negative pi over 3, it's that same distance, but in the negative direction. So whenever I find sine of negative pi over 3, it's the same as sine of 5 pi over 3. We would call negative pi over 3 and 5 pi over 3 coterminal angles. It means that that terminal side, the angle that points to our answer there, they're in the same place. So 5 pi over 3 is going to have the same sine and cosine values as negative pi over 3. Those are coterminal angles. Another way that you can do this, if visualizing it doesn't work for you, another way that you can do this, how many radians are there in one full rotation of the circle? 2 pi, right? So 2 pi. 2 pi is one full rotation of the circle. Or if we're dealing with degrees, it's 360 degrees, right? So if I have negative pi over 3, if I add 2 pi to it, that will be one full rotation on the circle, which means that we'll end right back up at the same place, right? Adding or subtracting 2 pi is always going to give you a coterminal angle, one of those angles that's in the same place, just called a different thing. So if you do that, you would have to get common denominators, which means you would have to multiply this by 3 on the top and bottom, which would give you 6 pi over 3. And if we do negative 1 pi over 3 plus 6 pi over 3, we will get 5 pi over 3. So that's another way that you can deal with this. If you have a value that is not on your unit circle, you can just add or subtract a full rotation as many times as you need to until you get a value that is on that unit circle. And so it's just adding or subtracting. It's a little tricky because you got the fractions, but it's just adding or subtracting. It's easier if it's degrees. So for example, if they had told us negative 45 degrees, we'd just have to add 360 to that, which would be a little bit easier. All right, so I've talked about those coterminal angles a lot, but the question is, what is sine of 5 pi over 3? And sine of 5 pi over 3 is the y coordinate right there. So it's negative square root of 3 over 2. Okay. Questions? All right, so here's another example that we've got, sine of 3 pi. 3 pi is not on our unit circle, right? So we've got some options here for the way that we can think about this. 3 pi, that's a positive 3 pi. Pi is half of the circle, so you could just visualize it. This would be pi, all the way around would be 2 pi, another half would be 3 pi. So it's the same as just the same location as just pi. The other option that you've got here, you can always add or subtract 2 pi. So 3 pi minus 2 pi would just give you pi. So sine of 3 pi is the same as sine of pi. And if I look at that unit circle there, Maddox, what would sine of pi be? It is 0. Very good. Because it is just your y coordinates there. All right. Now we've got cosine of negative 11 pi over 2. So for this one, if you're just looking at it visually, pi over 2 is a quarter of the circle. So what I usually do, because I think this is faster, I just do negative 1 pi over 2, negative 2 pi over 2, negative 3 pi over 2, negative 4 pi over 2, negative 5 pi over 2, negative 6 pi over 2, negative 7 pi over 2, negative 8 pi over 2, negative 9 pi over 2, negative 10 pi over 2, negative 11 pi over 2. So I'm just going backwards and counting how many pi over 2's I've got. So that gets me to pi over 2 right here. Your other option for that, just algebraically what you're doing there, is you're doing negative 11 pi over 2, and you're adding 2 pi, which would be 2 pi over 1. You would have to get common denominators. I'm adding because this is negative, and I need to get something that is on the unit circle, so I have to get a positive. So I would be really adding 4 pi over 2, which is 1 full rotation. So that would give you, if I do negative 11 plus 4, that is going to give you negative 7 pi over 2. Then you could add 4 pi over 2 again, because that's negative 7 pi over 2 is still not on the unit circle. That's going to give you negative 3 pi over 2. Again, still not on the unit circle. So you could add the 4 pi over 2 again, which gives you pi over 2. All right, so this cosine of negative 11 pi over 2 is the same as cosine of pi over 2. And if I go up here to the unit circle and look at pi over 2, Blaine, what would cosine of pi over 2 be? It is 0. Very good. Okay, questions? All right, so let's just see how we're doing. Summer, what would sine of 3 pi over 4 be? I mean, you can do that, pi over 4, 2 pi over 4, 3 pi over 4, but 3 pi over 4 is marked on your unit circle, so you don't have to do that. And what would our sine be for that one? Perfect. Just looking at that y coordinate, square root of 2 over 2. Now we're going to get in 7 through 10, we're going to get into some problems. All of these values are on our unit circle, but tangent, secant, cotangent, cosecant, those are not on the unit circle. But this is where we are going to use that stuff I gave you at the very end of class on Friday, which was, I was going to tell you where that came from. For our tangent, secant, cotangent, we said tangent of theta is going to be sine of theta over cosine of theta. Secant of theta is going to be 1 over cosine of theta. Cosecant theta is 1 over secant theta. And cotangent of theta is cosine theta over sine theta. Since these are kind of new too, I will put these up on the board for you tomorrow whenever we take our quiz, but you will eventually have to have these memorized. But tomorrow you don't really have to have anything memorized, you just have to know how to use it. So you'll be able to use your unit circles, and I'll put this on the board. Just really quick, I want to show you why this works. We know tangent of theta. It also is opposite over adjacent, right? Our regular trig, we know that it's opposite over adjacent. So if I think about this, if I'm doing tangent of theta and it equals sine of theta over cosine of theta, I know sine is opposite over hypotenuse. I know cosine is adjacent over hypotenuse. What do we do when we've got these complex fractions inside of fractions? Dividing fractions, easy as pie, flip the second, multiply. So what we would do here is we would do opposite over hypotenuse times hypotenuse over adjacent. And what could happen with our hypotenuses here? Hypotenuse. How do you pluralize hypotenuse? I'm not sure about that. We would cancel those out, and we would just get opposite over adjacent, which is, of course, tangent. So that's sort of like the proof of why that works. We could do that same thing for secant, cosecant, and cotangent, and it would get us back to those definitions with opposites and adjacents and hypotenuse. So I'm not going to go through and do all of those. just take me for my word that these are correct. When you do have to memorize these, tangent, you're just going to have to memorize it, sine over cosine. Secant and cosine, remember those were those reciprocal identities where they were flipped. One of them is one of them is adjacent over hypotenuse, the other is hypotenuse over adjacent. So it's just 1 over that value. You got to have a co with every pair. So secant is going to go with cosine, so that there's a co with that pair. Cosecant, I wrote this wrong. Make sure you've got it right on your paper. I think I probably did it right on Friday. This is sine of theta, not secant of theta. So make sure you've got that right. Hopefully I did it correctly on Friday, but you may have switched it now. So cosecant is 1 over sine. Cosecant and sine go together. There has to be a co. And cotangent is just the reciprocal of tangent. So it's just flipped from sine over cosine. These will be ones eventually you have to have memorized, but not tomorrow. All right, so I backed up there. So if I want to know tangent of pi over 4, tangent is not on my unit circle. I can't find the value of tangent just by looking at my unit circle, but I can figure it out. Because tangent of pi over 4 equals sine of pi over 4. Over cosine of pi over 4. And sine and cosine I can find from my unit circle. So you basically just have to take everything back to sine and cosine. Sine of pi over 4 right here is going to be square root of 2 over 2. And cosine is also square root of 2 over 2. What is square root of 2 over 2 divided by square root of 2 over 2? It's just 1, because anything divided by itself is 1. There. Okay, questions on those? So when we see secant of pi over 2, secant, we need to think of that being 1 over cosine of pi over 2. So on our unit circle, we're going to go to pi over 2. Our cosine value, what is our cosine value? It is 0, which is not good because can we divide by 0? No. So secant of pi over 2 is undefined. Okay, so that's something you got to be really careful with tomorrow. Usually students do really well on this quiz that I'm going to give them tomorrow, but the ones that I see most missed are ones that are 0 or undefined because they get those mixed up. If 0 is on the bottom, that is undefined. Okay, a lot of people put 0 on accident for that. And you won't have your calculator tomorrow, but just to show you, you do 1 over cosine of pi over 2. It's going to give you an error, divide by 0, that's your undefined. You can't use your calculator wrong. All right, yes? Yes, yes. So the calculator, so in Unit 5, we just always were in degree mode. In this unit, which there will be some things that we use the calculator on and others that we're not allowed to use the calculator. But when you are allowed to use the calculator, you've got to be really careful to make sure that whatever mode you're in, that has to be what you're plugging in. So I'm doing all of this in radians right now. There will be some degrees on your assignment, but I'm doing all of this in radians right now, mostly because I feel like radians are new and probably what we need to work with the most. But I could change any of these here to their degree equivalent. So like if I was doing sine of 3 pi over 4, instead of, I could do sine of 135 degrees and I'd get the same answer for that. But you would have to make sure if you're on your calculator, if you're typing in degrees, you need to be in degree mode. If you're typing in radians, you need to be in radian mode. So it makes it a little tricky because there will be some of both whenever you get to test time. So it makes it a little tricky. You've got to make sure that you're in the right mode for that. Okay. Cotangent, pi over 6. Pi over 6 is right here. Oh, let's see. Cotangent is going to be cosine of pi over 6 divided by sine of pi over 6. All right, so cosine is our x coordinate. It's square root of 3 over 2. And then our y coordinate for sine is 1/2. So for this one, I do not want you to leave your answer like this. I don't want this complex fractions. I also want the denominator rationalized if you need to. So dividing fractions is easy as pie. Flip the second and multiply. So the 2's here would cancel, and you would just get square root of 3 over 1, which of course is just square root of 3. For that. Let's do this last one together. I'm going to let you guys try the next ones. So cosecant of 2 pi over 3. 2 pi over 3 is right here. Cosecant is going to be 1 over sine of 2 pi over 3. And if we find sine of 2 pi over 3, we'll go to 2 pi over 3. Sine is our y coordinate, which is square root of 3 over 2. There. This is technically correct at this point, but you need to simplify it. So 1 times 2 over square root of 3. And that's going to give us 2 over square root of 3, but we need to rationalize that denominator, so we'll multiply by the square root of 3 on top and bottom. So we will get 2 square root of 3 over 3 for our answer. Questions? Okay, I want you guys to try the next 10 on your own there. So try the next ones that you have on your own. 12, you should get 2. 13 is 0. 14 should be negative 2 root 3 over 3. 15 should be negative square root of 3. 16 is going to be 0. 17 is negative 1. 18 is 0. 19 is negative square root of 3. And 20 is 2 root 3 over 3. Okay. Are there any that we need to see? Any questions? Yes, Hallie. 13. All right, so for tangent, we will be doing sine of pi over cosine of pi. And so when we look at pi, our y coordinate is our sine, so that's a 0 that we'll have on top. And on the bottom, we should have a negative 1. And so when 0 is on top, that's okay. It just equals 0 for that. Okay. Other ones you have questions about? Okay, we're going to take a little more class time to do some more practice on this. So you do not have to do the chart up there at the top. Just answer the questions. This one starts off with some in degrees. I didn't do any with degrees, but you're just looking at the degrees instead of the radians on your unit circle whenever you do those. And then it's basically just more practice. So go ahead and work on that for probably about 15 or 20 minutes, and then we'll check those. So when we draw that in, it's going to be a curve. So you're going to see it curved like this. And so that is what our function is going to look like. Now, this is what's so cool about sine functions, is that sine used to only mean triangles, and we used to only use it with triangles, right? But now that we have taken it and looked at what happens if we continue on past degrees past 180, right? Because triangles are limited to that 180 degrees. But when you think about the unit circle, where you can go around and around and around and around and around as many times as you want, if you graph these, it creates this graph that you see here. That's going to be a periodic function that keeps going forever and ever and ever, just up and down, up and down, up and down. And what's so cool about it is there's so many things in the real world that can be modeled using these types of functions that actually, apply in this particular, for these particular functions. So, like, if you think about one that you might be thinking about a little bit right now, ignore daylight savings time. Try to pretend that it does not exist, because separate from daylight savings time doesn't give us more daylight. It just changes it to where it's later in the day for us. So, but if you just think about the number of hours of daylight that you have every day. So in the winter, that number of hours of daylight is really, really low, right? So you're going to have, the sun comes up a little bit later. It certainly goes down much earlier. And so all winter, it kind of seems like it's about the same to me. Yeah, I'm sure we could look at numbers and actually see what's happening. But all winter, it seems like it's about the same. And then spring gets here, and it's like all of a sudden, even before daylight savings time, the days get longer and longer and longer. Because look at what's happening right here. Your line's a lot steeper right here. That change is happening a lot faster. But then when we get to summertime up here, when we have longer days, to me, it seems like all the days in the summer are about the same, right? You're going to have your longest day. When is the summer solstice? Is it June? No. When is summer solstice? Maybe. Somebody give that a Google real quick. June 21st, yes. So, this peak right here, that's June 21st. But all those times around it, like, yes, that is the longest day, but it doesn't seem like the few weeks before or a few weeks behind are much different. Because, see, it's not very steep right here. You got a little bit of change, but not drastic change. So it's not like we get, 5 minutes of daylight added every day that would make like a straight zigzag like this. It's a sine curve. So you have a few more minutes in the day, but not a lot. But then whenever it gets time for winter to come again, in the fall, it seems like it starts dropping off quick. Although daylight savings time does sort of change our perception of that as well, because whenever you hit daylight savings time, it sometimes seems like you have a lot less daylight, or more daylight, depending on whether it's being enacted or going away. But the hours of daylight just keeps following that. There's lots of other things that apply here. Things like ocean tides can be modeled with sine curves really well. all kinds of like natural phenomenon that it seems like should not be related to triangles at all, right? So it's kind of cool where these things can be applied. They're really useful in all kinds of situations where you see repetitive motion. So that's kind of cool. So I want you guys to do cosine for me also. So same thing, but for, oh wait, hold on. Before we do cosine, let's talk about a few things for this. Let's talk about the period, the domain, and the range for sine. So the period is the length of time it takes to repeat. So if we start right here, I usually start from 0, 0, and we go up and back down and then back up. How far do we go before our pattern starts to repeat? It's not pi. It is 2 pi. Because our pattern, although it's just like mirrored, it is different right here from negative pi to 2 pi because you're below the x-axis right there. Which, if you think about it, with your unit circle, that should make sense because that's the time it's going to take you to go all the way around the circle. And then after that, you're just going to start repeating over and over again the more times you go around the circle, right? Because 2 pi would be a full rotation. So our period would be 2 pi. The domain for this function is going to be all real numbers or negative infinity to infinity because this just goes on forever and ever and ever. That unit circle is just going to keep going around and around and around and around. You can do 2 pi over, or you can do 2 pi, 4 pi, 6 pi, 8 pi. You can keep on going forever, go backwards. So you have an infinite domain for that. What about our range? It is negative 1 to 1. Do I need parentheses or brackets? Brackets, because it does actually include 1, right? It gets up to 1 at that point and equals 1. So we would do negative 1 to 1 for that range. Or we could write it this way. Negative 1 is less than or equal to x. Less than or equal to 1. And we talked about this a little bit earlier when we were doing law of cosines. It has to be between negative 1 and 1 because whenever we're talking about sine of theta, it equals opposite over the hypotenuse. And the hypotenuse has to always be larger, right? So you always, it makes you think you should always have, like it shouldn't actually equal 1. And in a triangle, it's never going to equal 1. But theoretically, you could have two 90-degree angles, which really doesn't make a triangle anymore, and then that would be where you get that value of 1 right there, which is a little, it's odd to think about with triangles, but if you think about it with that unit circle, where those points line up there at 90 degrees, you hit 1, it makes a little bit more sense. So you can never get a number larger than 1 whenever you're taking sine of an angle, or less than negative 1. Okay? All right, so I want you guys to do the same thing for cosine. Give you a few seconds to do that.